Okay, so we are also online on Zoom. This is the thematic session on the eProcessor, titled "The eProcessor is 5 Hardware Software Ecosystem." We are a EuroHPC European project. My name is Nehir Sönmez. I'm the coordinator of the project. By the order of appearance, today we are presenting five of us. Myself, Pedro from Chalmers, Kevin from Bielefeld, Luke and Leonardo from BSc. Um, Before I start, I would like to thank the organizers for this amazing event. Everything was perfect and ran very smoothly. And thank you so much. This is a great city, and it's been a great pleasure. So, okay. Today, the agenda is that I will do a quick introduction on the processor project. Then we're going to talk about the hardware. Um, there's the architecture RTL part, the FPGA part, and the chip fabrication PCB part that will be presented. We will do a short Q&A after the hardware part, and then we'll move on to the software. We'll do the application use cases, and then tools, OS and system software, and then we'll finish with the Q&A. So what is the eProcessor? The eProcessor aims to build a new open source out-of-order processor and accelerators and deliver the first completely open source European full stack ecosystem based on these. The E comes from the wildcard. E comes from extendable, open source, energy efficient, low power, extreme scale, high performance, suitable for uses in HPC and embedded, and extensible, which means easy to add on-chip, off-chip components. As I said, it's a combination of RISC-V, ISA, applications and system software that we want to hopefully in the future use as building blocks for future HPC systems. We're doing software hardware code design for improved performance and energy efficiency. We're looking into HPC and high performance data analytics applications. That means AI, ML, bioinformatics. We're also doing architectural simulations and FPGA emulation. And most importantly, we're going for two ASIC tapeouts. One will be a single core. By the end of this year, we will have sent it out. And one will be a multi-core tapeout next year. So the consortium looks like this. BSc is coordinating. We have Chalmers, Forth, Unirome, Cortus, Christman, Bielefeld, Extol, Thales, and Exapsys. We have 5 industrial partners and 5 academic partners. It's a balanced consortium. As I said, it's a EuroHPC 2019 call, 3-year project, 8 million euros. We're on month 13. So an overview of the approach. As I said, at the top we have the software layer. We're doing HPC, AI, and bioinformatics applications. We're doing that in a code design approach. And then underneath we have tools, compiler, performance monitoring, debugging, and runtime, OpenMP, TensorFlow, and of course Linux. Underneath we have the hardware layer. We're doing mixed and reduced precision. We're doing 6432, 16-bit, and 8-bit mixed precision, and also 84 to perhaps 1 of integer precisions. And also we're doing a 2-way out-of-order multi-core and low power and accelerators. So we're going for a multi-socket cache coherent implementation. We are featuring things like adaptive caches and fault tolerance throughout the stack. That's on the right side of the figure. And as I will present, we're doing on-chip vector AI and bioinformatics accelerators that are coprocessor that have reduced and mixed precision floating point. and also cache coherent off-chip CNN accelerator. Quickly going through what each partner is doing. Quartus is providing the out-of-order core. They're also leading the physical design. BSC is doing vector accelerator, HPC applications. This is not a complete list, but just to have an idea. Chalmers is doing the NOC. They're doing the AI hardware, FP16, 16-bit floating point. The home node, they're also leading OS and runtime work package. Forth is doing the L2 cache that can also work as a scratchpad. They're also doing an IO MMU for RISC-V, which provides MMU capabilities for IO devices. They are also leading the FPGA work package. Uniroam is working on hardware, mixed low precision floating point, 8-bit. Bielefeld is doing the PCB. They're also doing the smart mirror application. Xtol is doing the chip-to-chip coherent link. Thales is doing aerial surveillance application, plus they're providing an off-chip accelerator for us to test it. Christman does bring up deployment and the board support package. And Exapsys is doing architectural simulations with GEM5, and they're also the exploitation and the dissemination lead. In terms of milestones, we just did the second milestone, which was a RTL freeze for the first tape out that was done at the end of last month. It was a soft RTL freeze. We have a bit more features to add, but the project is going fine. We're going for a tape out by the end of this year. And that will be a single chip tape out. Many reports due, of course. The emulator would be made available. I think the first release of the open source core can also be done by the end of this year. And then next year, around end of June, we're doing the freeze for the multi-core implementation. And then towards the end of the project, we're, of course, getting the tape out back, evaluating it, writing the reports, and wrapping up. In terms of work packages, BSC is coordinating work package 1. Work package 2, Yanis from Exapsys is leading dissemination and exploitation. Work package 3, Luke Alvarez from BSC is leading software application use cases and evaluation. Work package 4 is led by Michael Pericas from Chalmers. That's on tools, OS, and system software. Work package 5 is led by myself. It's the architecture, RTL, and verification work package. Work package 6 is on system simulation and FPGA emulation, led by Forth, Vasilis. And work package 7 is led by Quartus, Christoph. That's on chip fabrication, PCB, and validation. We have the applications at the top, the tools OS, and then the hardware layer, work package 5, and work package 7 is the physical layer. There's the hardware emulation aspect to it, the software simulation aspect to it in work package 6. And this part on the right is that the dual socket configuration can work as 2 cores connected to each other, or 1 core and 1 off-chip accelerator, which should be socket compatible, and we're going for such an organization. In terms of collaboration with other projects, there's many of them. You can see them on this slide. Just maybe one thing to mention is from EPI, we are taking some of the IPs as a baseline. We are extending them. And also there's other stuff such as the Legato PCB and the use case application. We will touch on these, but I should move. So that's the end of the first slide deck. So as I said, we will first do the hardware. Let me go to the hardware and talk a little bit about how the hardware IPs look like. I will start with the single core processor design and implementation. Then Pedro will present the accelerators. And then I will get back to RTL verification test benches, the multi-core design implementation, and the Encore IPs. So yeah, the out-of-order processor core, that's a two-way RISC-V out of order, the GC ISA with various privilege levels. It's a 4-way issue, 6-way retire core. It can sustain 2 data memory operations per cycle throughput, and 4 memory operations can be dispatched per cycle to the load store unit. So it's provided by Quartus. They can do snapshots of the return address table branch history to quickly recover from mispredicted instructions. They can reorder memory operations, but always respect the RISC-V weak memory ordering. There's a unified register file supporting different paging. And we are going for 2 gigahertz in 22 nanometer technology. For the second tape out, for the first one, I think we want to get the integration and the IPs right. So we're probably going for a 1 gigahertz target in the first tape out by the end of this year again. And the core reaches 6.64 core marks per megahertz. And work is still going on. We have a first internal release and looking to improve that and also to connect to the rest of the components. A bit of the first FPGA mapping of that. We're targeting a VC128 FPGA. It takes about 275K lookup tables, which is around 1/5 of the FPGA. So not too large. Also, although pretty good size of a core. Again, we're working on mapping this better. We need to do some more iterations, but work in progress.